Welcome to CSC 201, section 11.2, big O, big omega, and big theta notations. So we have two new Greek letters we're going to be using today. They are theta, this is capital Greek theta, and capital Greek omega, theta and omega. So I'll be using those words to describe these symbols. Okay, we have three definitions here, totally brand new. It says, if for sufficiently large values of n, the values of f are greater than those of a positive multiple of g. So we just studied positive multiples of a function. It just makes the function taller, stretchier, or shrinks it if the multiplier was a small number. Okay. So for sufficiently large values of n, the values of f are greater than those of a positive multiple of g, then we say f is of the order at least g. And the notation is that f of n is omega of g of n. So of an order at least g. So here's a picture of it. So this black curve here, that is a multiple of g. So they wrote a times g. So a is the multiplier. So this is some multiple of g. And f, after a certain point, okay, f is larger than it. Okay, so if f is larger than a positive multiple of g, so over here the blue is above the black, it has to just happen at some point. It doesn't have to always be true. You can ignore some stuff at the beginning. But then after some point, it has to always be true. Okay? So f is larger than a multiple of g. So we say f is of order at least g, or f is omega of g. All right, so now the reverse. If, for sufficiently large values of n, the values of f are positive, and they're less than those of a positive multiple of g. So here I have a positive multiple of g again, and my f values are smaller than it. Okay, so reverse here. Here I had my multiple of g, and my f values were larger. Here I've got my multiple of g, and my f values are all below it. Okay. In that case, we say f is of order at most g, and we write f is big O of g. Okay, so this one is f is big omega of g. I forgot to say the big because it's capital. F is big omega of g, and here we say f is big O of g. And then we combine those two, and we say if for sufficiently large values of n, the values of f are bounded both above and below by positive multiples of g, then f is exactly of order g, and we would write f is big theta of g. So if you can sandwich f between two different multiples of g, two different multiples of another function g, then we say f is big theta of g. Okay, so those definitions are pretty abstract. So I think we should do some examples and use those notations and those words to just figure out what they're saying. So I want to use the big O, big omega, and big theta notations to express this statement. So I've got this polynomial, 17n to the 6th minus 45n cubed plus 2n plus 8. And I have it sandwiched between two different multiples of n to the 6th. It's larger than 4n to the 6th, but smaller than 30n to the 6th. So being larger than 4n to the 6th means we say that the polynomial f, so we say 17n to the 6th minus 45n cubed plus 2n plus 8 is at least order n to the 6th. Okay, so that's this inequality says that. And the notation is that 17 n to the 6th minus 45 n cubed plus 2n plus 8 is omega of n to the sixth. Okay. And then if I look at the other inequality, this part, 17n to the sixth minus 45n cubed plus 2n plus 8, it's smaller than or equal to a multiple of n to the sixth. So that means it is big O of n to the sixth. And since the polynomial is both omega and big O, big omega and big O of n to the sixth, that means it is theta of n to the sixth. It is of the order of n to the sixth. I should have left a little more room here. So I'm going to say 17n to the sixth minus 45n cubed plus 2n plus 8 is theta of n to the sixth, which means, i.e., 17n to the sixth minus 45n cubed plus 2n plus 8 is of the order of n to the sixth. Okay, number 6, I want to show that 15n cubed plus 11n squared plus 9 is big omega of n cubed. All right, so that means I need to say that I need a multiple of n cubed that is smaller than this polynomial. And I think 15 will work, right? So if I write 15n cubed, and I want to compare that to 15n cubed plus 11n squared plus 9, because n is bigger than or equal to 3, then 11n squared plus 9 is a positive quantity, which means that this quantity is larger than this quantity. So I can write that, and that tells me that 15n cubed plus 11n squared plus 9 is big omega of n cubed, okay, because this polynomial is larger than or equal to a multiple of n cubed. All right, so now I want to show that same polynomial is big O of n cubed, which means I need to write 15n cubed plus 11n squared plus 9. I need to do an inequality in the other direction. It needs to be less than or equal to a multiple of n cubed. So 15 won't work in this case. But what I could do is, because n is positive, I know that for sure 15n cubed plus 11n squared plus 9 is smaller than or equal to 15n cubed plus 11n cubed plus 9n cubed. Okay, because n is bigger than or equal to 3, squaring n will definitely, cubing n would be larger than squaring n, and cubing n would be larger than raising n to the 0 power. So this is true, and then that equals, well, I'm going to write less than or equal to because it does have the equals as well. Let's see, that's 35n cubed. Okay, so 15n cubed plus 11n squared plus 9 is smaller than or equal to a multiple of n cubed, which means that 15n cubed plus 11n squared plus 9 is big O of n cubed. So the ideas developed in this section, measuring the order of a function, are used to measure algorithm efficiency. And if you're interested in how it works, I encourage you to read 11.3. But we won't actually be covering that material in class.